You are watching for the greater good.
Hello guys, and welcome to our channel for the greater good. Today we'll be discussing a very interesting topic, that is sparse matrix. To understand sparse matrix, we first need to know what a matrix is. A matrix is a set of numbers arranged in rows and columns so as to form a rectangular array. The numbers are called the elements or entries of the matrix. In computer programming, a matrix can be defined with a two-dimensional array. Matrices with high proportion of zero values are called sparse matrices. We'll be discussing two general cases of sparse matrices. The first one is triangular matrix. Triangular matrix is a special case of a square matrix. In lower triangular matrix, all the entries above the main diagonal are 0. This guy highlighted with the red color is the main diagonal, and all the entries above it are 0. In case of an upper triangular matrix, all entries below the main diagonal are 0. The second case is tridiagonal matrix. In a tridiagonal matrix, all entries on the main diagonal and the entries immediately above and below the main diagonal are non-zero. The diagonal highlighted with the red and green color are the non-zero entries. In this video, we'll be discussing how to convert a tridiagonal matrix into a unidimensional array, and how to retrieve a triangular matrix from a unidimensional array. But first, we need to know why we have to convert a triangular matrix into a unidimensional array. When a sparse matrix is represented with a two-dimensional array, we waste a lot of space to represent that matrix. For example, we consider a matrix of size 100 by 100 containing only 10 non-zero elements. In this matrix, only 10 spaces are filled with non-zero values and remaining spaces of the matrix are filled with 0. That means totally we allocate 100 by 100 by 2, that is 20,000 bits of space to store this integer matrix. And to access these 10 non-zero elements, we have to make scanning for 10,000 times. To make it simple, we convert this matrix into a unidimensional array so that the zero values are ignored. Assuming a very large sparse matrix can fit into the memory, we'll want to perform operations on this matrix. Simply, if the matrix contains mostly zero values, that is no data, then performing operations across this matrix may take a long time, where the bulk of computation performed will involve adding or multiplying zero values together. Consider a lower triangular matrix A. The implementation for a lower triangular and an upper triangular matrix is almost the same. We have taken a lower triangular matrix as an example, but as we proceed through this video, I'll be discussing the implementation for an upper triangular matrix as well. Now we'll omit all the zero entries from this matrix. The first row of this matrix will be containing one non-zero element, the second will be containing 2, third 3, fourth 4, and so on. So as we can see, this makes an arithmetic progression. The total number of non-zero elements will be the size of the unidimensional array, and the sum of the number of entries in each row can be calculated through the formula of summation for arithmetic progression. Here I have calculated the general formula. It will be half into n plus 1. Now let's dive into our algorithm. to store a triangular matrix into a unidimensional array. Now I is the index of the unidimensional array, j is the index of the rows, and k is the index of the columns. As we saw earlier, the number of non-zero elements in the first row is 1, number of non-zero elements in the second row is 2, number of non-zero elements in the third row is 3, and so on. So for each row we'll iterate the columns. So when j is equals to 0, we'll iterate only see the 0th index of the row, and when j is equals to 1, we'll see the 0th and the first index of the row, that is the column. So in this way, when j is equals to 0, 4 will be mapped to the unidimensional array. When j is equals to 1 and k is equals to 0, 3 will be mapped to the first index of the unidimensional array. In this way, all the elements of the non-zero elements of the triangular matrix will be sequentially mapped to the unidimensional array. You might have noted that wherever the value of k is greater than j, the entry is 0. In case of the upper triangular matrix, the converse would have been true. And some of you might have been wondering that why there is a 0 inside the unidimensional array. The reason is that when j is equals to 3 and k is equals to 1, there is a 0 among the non-zero entries, so it will be mapped into the unidimensional array. Now we'll move to the second phase of our video. Here we'll convert a unidimensional array into a lower triangular matrix. The condition here is, if value of k is greater than j, then the resulting entry will be 0. Otherwise, we will sequentially pick an entry from the unidimensional array and map it to the lower triangular matrix. If it was an upper triangular matrix, the condition would have been reversed, and the if statement would have been that if k is less than j, the resulting entry will be 0. Let's dive into the algorithm. Okay, now we'll see the mechanism behind this algorithm. When j is equals to 0 and k is equals to 0, we'll pick an element from the unidimensional array that will be the 0th index element. This element is 4. For all the other elements in this row, k is greater than j, so they all will be 0. Now, when j is equals to 1, k and k is equals to 0, k is less than j, so we'll pick an element from the unidimensional array, and the next element is the first index element, that is 3. When j is equals to 1 and k is equals to 1, they both are equal, so we'll go with the else condition, and the second index element from the unidimensional array will be picked. Rest of the elements in this row will be 0. Similarly, 3 elements will be picked for j is equals to 2. In case of j is equals to 3, k won't be greater than j for any value, so 4 elements will be picked for j is equal to 3.